All right, OBS is on, so we are ready to go. So I forgot to mention one thing about the homework assignment. I did not designate which one is the destination, but some of you guessed the right one because it is the destination vertex is D. It kind of implied by, there's nothing coming D. There's nothing coming out of D, but everything kind of goes to D. So D is the destination, and I have added that to the homework assignment. So when you refresh your assignment description, it should be there. So right here, the last sentence of the first paragraph now states that vertex D is the destination vertex. Okay, and this graph is a little bit easier compared to the one that I did in class. It has fewer vertices and definitely a whole lot fewer edges. So are there any questions about this homework assignment? It's due on Monday, next Monday. So you got basically another 4 or 5 days to work on it. But are there any questions? Yep. Um, it's very likely to be the last one because next Wednesday is the last day of lectures. So I won't have enough time to go over solutions if I give you any additional homework assignments. So that's the problem. I would like to give you guys more, but there's not enough time. Okay, yep. I do not need a picture of the graph. Just the trace, the same way that I did in class. So I know some of you are taking 430 and the way the algorithm works in 430 is a little bit different. You just have to kind of do it the same way that I did in this class, so it's kind of specific to this class. And if I understand correctly, the algorithm used in 430 has to designate a start vertex and a destination vertex. Okay. And this one does, can handle multiple destination vertices and it find the shortest path from every single vertex to a destination. The shortest one, the one that's closest to every single vertex. So from that perspective, this algorithm is actually slightly more general because it can find, the shortest path between all vertices. Yep.
What if I noticed when you did the spreadsheet last time,
Mm-hmm.
each of the neighbors of the destination
Mm-hmm.
had more neighbors, more incoming neighbors. But on this homework, let's say B, one of the neighbors has no incoming neighbors, so just that one neighbor.
If it has no incoming neighbors, you still have to take it out of Q. It's just that the for each loop inside the while loop has nothing to do because it has no incoming neighbors.
Okay, just the destination and one incoming neighbor, and that's it.
Yep. So on the in the trace, there's nothing to show because you still have to show that you pick out this neighbor, you consider that incoming neighbor, but there's nothing to do. There's nothing to update after that.
So you still take it out of Q.
Yep. Yep.
Are the paths only one direction as specified by the tuple?
Yes.
Okay.
So all the edges, not paths. So the edges are directed. Yes.
Okay.
A path is a walk that has no repetition of vertices nor edges. So that's why when we find a quote unquote shortest path, it is implied that it has no there are no loops of any kind because you cannot repeat an edge nor a vertex in a path. And if you traverse a graph, okay, any traversal using edges, if you're following the direction of the edges, so if you go from a vertex to another vertex to another vertex to another vertex, as long as you're following the edges, it is called a walk. So a walk can have, can be cyclic, because you can kind of go around and go back to the same vertex and go somewhere else, but a path cannot. Yep.
What if you have more than one shortest path?
If you have more than one shortest path, then finding um, the the Dijkstra's algorithm will only identify and use one in the solution, but it will, depending on how you expand, how you pick your items from Q, it may choose one instead of the other one, but they are all considered correct because they actually have the same length.
So the actually in the E prime,
Mm-hmm.
both paths might be included.
No, cannot be, because E prime, the graph, the solution graph that's made out of V and E prime is guaranteed to be a forest. In other words, it is a bunch of trees, but when you have a bunch of trees, it is guaranteed that you cannot have two paths from one vertex to another vertex. So, the Dijkstra's algorithm is only guaranteed to find one of the many potential equivalent length shortest paths. Is that okay? All right, cool. Any other questions? No other questions? All right. So the final exam is 2 weeks from today. The time of the final exam is from 12:45 to 2:45. Okay? So it's a little bit longer than a usual lecture period, but you guys know that already because you're in this class. This is not your first class at AR for most of you. Yep. In the Los Rios district too? Because we all follow the same kind of final schedule. Each campus has a slightly different schedule based on, what time of the day for which class. But I think, all final exams are 2 hours long for semester-long classes. Okay. Any other questions about the Dijkstra algorithm homework assignment? No other questions? Is anyone done with it already? Assuming, vertex D is the destination? No, not yet. I don't think it's nearly as long as the one that I did in class. So, I don't think it's going to take too much time. It's only a matter of, following the algorithm to get it done. So are we good so far? All right. Are there any questions about the Astar algorithm, which we started to trace in the previous class, but we have not finished it? So do we want to finish that one, or do we want to just kind of go like, yeah, we kind of know what it is? We want to finish it? Okay, let's do it. All right. So I think the graph or the graphical representation is still on my tablet on that last page for this class. So we'll start with that. Okay. Oops. Okay. My eyes are really up and running. Lecture notes. And this is cisp440. Yep, there we go. So this is the graph that we have been working with. And I think last time I kind of mentioned that the way that I trace an algorithm makes it pretty easy to pick it up, from like a few days later. So we'll see whether that claim is true or not. So let me go to the share folder, and I think I named that based on the date of that particular class. So here we have the partial trace. We're partially done. So at this point, okay, let me zoom in a little bit because that is a little bit too small. That's a little big, but I think that's fine. Okay. So this is the row 7 is basically the current state of the trace. We still got 2 things in big O, the set O. So that means we're not done yet. Okay. So this is the trace. And then we'll go take a look at the algorithm. The algorithm is here. And for the most part, we are done with all the initializations and stuff like that. So we are really just running the loop itself, which is starting with, is big O empty? Nope, it's not empty. So it satisfies the first requirement to stay in the loop. The second question is, can we find any vertex in V so that f of V is less than g of x, x being the destination? So we go into the, we look into the trace. So let's see, the trace is here. And I'm going to break this out into its own window and maximize it. There we go. So when we look into, oops, active site, wrong class. Okay, so when we look into the f values and we look into g of x, what is g of x at this point? Well, this is column E is the function g, column f is the function f. So g of x is infinity. In other words, we still haven't found a path, okay, let alone the shortest one, but we still haven't found a path to get to the destination from the start vertex. Okay. So now the question is, do we have any f value that is less than infinity? Let me go back to the algorithm first. Okay, I think the algorithm is over here. Okay. So we are basically asking this part of the question, is there at least one vertex such that f of v is less than infinity? Because we know g of x is infinity at this point. So we check out the trace, we look into f, and we got plenty of vertices with a f value that is less than infinity. So that means we have now satisfied both conditions of the while loop, and we have to go for another iteration. All right, so getting back into the algorithm itself. So we are now into the first part of the while loop. Let C be an element in O such that it has the smallest f value of all the vertices in big O at this point. So we go back to the trace and then we look at all the f values and we ask, okay, out of A and E, which one has the smallest f value? A has an f value of 5, E has a f value of 6. So we're going to pick A, vertex A, to be my variable C in the loop. So we update C, and we say, okay, we're going to pick vertex A as my C at this point. So that means I have to immediately update my big O set so that so that A is not a part of that set anymore. So every time we pick something from big O, we have to take it away because now we are exploring that particular vertex. So are we still working? Is it still okay so far? So the idea of using the one that has the least f value is basically it's the hallmark signature of a greedy algorithm. We're just looking for something that seems to be the best. Okay, this is the best option. It looks the most promising, so we look into that first. Okay. So now we switch back to the algorithm. We are done with this part here. Let's see in O, blah, blah, blah. We are done with the second part. We removed that particular vertex, vertex A from big O. So now we have to look into every single outgoing neighbor, okay, neighbors that are connected to from vertex A. And for each one, we have to go through this type of calculation. So we go back to the graph and we ask the question, how many neighbors do we need to consider? We got B as a vertex coming out of A. We also got X as a vertex coming out of A. Now, in this case, there's no need to say, okay, we have to prioritize which one over which one. There's no sorting whatsoever. We have to look at all of them anyway. Okay? So which one do you guys want to look at first? Vertex B or vertex X? Because we are looking for the outgoing neighbors from vertex A. X? Okay, we can look at X first. There's no reason why we have to look at B first. So we go to the trace here, and then we say, okay, in the for each loop, we want to consider X as a neighbor of vertex A first. Okay? So now we have to compute the variable T, which is at the last column here. And according to the algorithm, T is just the sum of G of A in this case, plus the distance from A to X. Is that okay? In other words, what we're trying to do is to say, what is the length of this path? Starting from the start vertex, going through vertex A to vertex X, which is my destination. Well, it so happens to be the destination, but this is the actual length of that path. Okay, so what is g of a? Okay, let's check it out. So when you look at g of a, it is 3. What is the distance from a to x? So for that, we have to look at the graph. It is 4. So 3 plus 4 is 7. So we have to update the g value. Okay. Oops, excuse me, I take it back. We don't update yet, okay, but we do have to update t. So t is now 7. The next question is, do we need to do any updates? Because we have to evaluate the condition of the conditional statement now. So we are asking, is t, which has a value of 7, less than g of x, which has a value of infinity? Is 7 less than infinity? Yes, it is. Okay, so we got a bunch of stuff to do now, because we just found a shorter path to a vertex. Okay, now vertex x so happens to be the destination, but the destination doesn't get any special treatment. It is just considered as, oh, okay, we found a path to a destination, to a vertex now. Okay, so we go through the same usual stuff that we have to do here. The first thing is we have to add vertex x to big O, the set of big O. Okay, so let's do that. So as a result of that, this is now getting updated. E and x are now in big O. That's the first thing we do. The second thing is I want to update the previous of vertex x to vertex A in this case. So we go to the previous function, and then we modify the function so that the previous of x is no longer undefined. Instead, it is a. Okay, so in the path that I'm looking into right now, vertex A is right before vertex x. Is that okay? So when you look into column D, these are not edges. This is actually the representation of a function, not edges. All right, so we got a few other things to do. We got to update the g value and the f value. The f value, the g value is the easy one to update because we just use t to update the g value. So we just copy and paste this, change the value that x is mapping to, and we change that to t, which is 7. In other words, we're remembering that, oh, we just found a path going from the start vertex through A to vertex x, and it has a length of 7. That's what we are trying to remember here. And then f in this case is kind of easy to remember too, because it is really just g of x plus the heuristics of going from x to x. So what do you think is the proper underestimate of distance going from vertex x to vertex x when the estimate cannot go negative? It has to be 0. Is that making any sense? So g of x in this case is the same as f of x, which is 7 also. Are we doing okay so far? Yes? Okay, all right. Well, we got another vertex that we have to consider, which is B, because B is also an outgoing neighbor from vertex A. So the first thing is we have to compute t. So switching back to the algorithm, the value t is g of a plus the distance from vertex A to vertex B. So looking at the graph, let's figure out what it is. So AB has a distance of 1. Okay, cool. And looking at the trace, we look at g of a. G of a is 3. 3 plus 1 is 4. So in this case, your t equals to 4. Now we have to ask the question, is t, which has a value of 4, less than g of b at this point? So we have to figure out what is g of b at this point. So for that, we go back to the trace. We look up the g value of b. It has a g value of infinity. In other words, I have not seen a path from the start vertex to B yet at this point. This is the first path I have found. Not necessarily the shortest, but I found a path now. Well, infinity is definitely greater than 4, so we have to go into the conditional statement and do something. Okay, first thing when we get into the conditional statement is to say, oh, we can add your vertex b to the set now. That's the first thing. Second thing is to set the previous. Okay, so we update the previous function so that the previous of b is vertex a as well. Then we go to function g. We update this and we say, yep, we found a path to vertex b and it has a length of 4. And then we also update function f so that the value that b maps to is basically g of b plus the heuristic from b to x. Okay, so let's look up the graph and find out what that is. So according to this graph, the heuristic from b to x is 1. Okay, it's an underestimate, okay, because the actual distance is 2, but 1 is an underestimate. That's fine. So that's why the h value of b is the g value of b plus 1, so that will make it 5. Do we have any questions about this particular update? Is that all good? Okay. So at this point, we have explored all the outgoing neighbors of A. So we exit the for each loop. We go back to the while loop. So when we get back to the while loop, we ask the same question again. Is big O empty? It is not empty, but we have a second condition. The second condition is saying, are there any f value of any vertex in V that is less than the g value of x? The g value of x is 7 at this point. So the question is, are there any f values that are less than 7? So we go to the trace and then we look it up. Okay, these are the g values. G of x is 7. So we look at all the f values. Oh, we got a whole bunch, right? We got a whole bunch of f values that are less than 7. So that means we cannot stop yet. The semantics of that condition is to say, can we potentially have a path that is shorter than the current known path to the destination? That's basically what it's asking. If there's at least one vertex with an f value that is less than the g value of x at this time, it means, yep, we might have overlooked something. There may be a path that is shorter than the one that we have found at this point. So that's why that condition is also needed in order to stay in the loop. All right, so now that we are deciding to stay in the loop, we have to pick one vertex out of E, X, or B to explore. But the criteria to pick that one is who has the smallest f value among these three. F of A is 3, f of x is 7. Oops, A is not even one of the options. We got E here. So f of E is 5, f of x is 7, f of B is 4. So we're going to pick 4 because 4 has the smallest f value, which means it looks the most promising as one of the vertices along the shortest path from the start to the destination vertex. Is that okay? Yep.
We're looking at the g or the f function.
We're looking at the f values, not the g value. The reason why we're looking at the f value, not the g value, is the g value is exact, okay? It is telling you what is the currently known shortest path, what is the length of the currently known shortest path from the start vertex, but only to that vertex, not all the way to the destination. The f value, on the other hand, is an estimate, okay, based on what is the actual length of the known shortest path from the start to this particular vertex, but it also adds the heuristic from this vertex all the way to the destination. So it is an estimate of, if you go through me, I'm guessing the path is going to be this long, okay? So we pick B, and then we have to look at every single outgoing neighbor of B in this case. So we look at B, and that's pretty easy. B only has one outgoing neighbor, and that turns out to be X. Okay, cool. So we go here and go like, okay, X is the only outgoing neighbor of B. then we have to compute the value t, which is based on g of b plus the distance of the edge bx. Okay? And the distance from b to x is 2. Okay? The g value of b is 4. 4 plus 2 is 6. So t is now 6 here. And determining, in order to determine whether we execute the then part of the conditional statement, we have to perform the comparison. So we are comparing 6, which is the value of t, to the g value of n, which is x. Okay? So g of x has a value of 7, and t only has a value of 6. 6 is less than 7, so that means we are going to go into the conditional statement, and because we have just found a shorter path to go from the start vertex to vertex x. Yep.
That g of x, that's f of x.
Say that one more time.
That's g of x, and that's f of x, right?
Column E is g of x, and then column F is f of x.
But you were saying otherwise.
Did I?
Yeah.
Huh, okay. So g of b is 4, and then plus 1. Oh, okay, I see. So this is 5. Okay, thank you. I'll take it back. This is 5 because it's based on the g value plus that 1, the distance. Okay, thank you. But 5 is still less than 7, so the decision was right, but the number was wrong. All right, so first thing first, we have to change the previous. In other words, the shortest path to x is no longer going through A because we just found a shorter path going through B. So we're updating the previous of x in the solution graph to be B. We have to update the g value because the actual length of the shortest path currently known to go from the start vertex to x is no longer 7. It is 5. And the h value is updated accordingly. It's the same because this is the destination vertex, and h of xx is guaranteed to be a 0 because the destination is at the distance of 0 from itself. So the underestimate cannot be greater than 0, but since it cannot go negative either, so 0 is the only possible hxx. So we're still doing okay so far with this, all this update. And technically speaking, I'm also going to union this particular set. Oh, I forgot one thing here. Once I picked B, I have to remove B from the set, so it only has E and X left. So over here, I'm really adding or doing a union with X again, except we cannot see it because the set O already has the element X in it. So by doing a union with a set that only has X as an element, it gives me exactly the same set. Okay. Cool. And B has no other outgoing neighbors, so we are done with the for each loop, so we're going back to the while loop. So if you remember, when we go back to the while loop, we ask 2 questions. Okay. The first question is O empty? Nope, it's not empty. We got 2 elements left in it. The second question is, are there any f values that are still less than the g value of x? The g value of x is 5. So are there any f values that are less than x? So we got a, b, being less than x, even though they're not in the set of O. So we have to go for another iteration. So this time we're going to pick E. So this time we're going to pick E, and then we ask, do we have any I'm just thinking, whether the algorithm can be optimized. Okay, let me show you the algorithm here. So I'm just thinking whether the algorithm can be optimized by changing this condition so that V is not an element of V, but an element of O. In other words, if there are no more promising vertices in O, then we don't have to do anything any further at this point. Let me switch back here. Something doesn't seem right. Sorry? F. Yeah, we're comparing F to G, but S still has a value of 4. No, but S is not a part of the. Yep. So basically, this is reflecting that the last time we update the F value of S, it makes it still look more promising than it really is. But because it's no longer in the frontier set of O, I can't pick it, to re-expand it. So that means, my algorithm, even though it is not incorrect, but it may not be optimized either. In other words, I should be able to stop now, because this, if I change this V to big O, then we are done. Because between E and X, F of E is not less than G of X anymore. And F of X itself cannot be less than G of X either. So we're basically done. So the question now is, have we found the shortest path? We claimed that the shortest path, okay, let me go back here. So we claimed that the shortest path has a length of 5 right here, because the G of X is basically the length of the shortest path. So when we go back to the actual graphical representation, is that the actual shortest path? A length of 5. Cannot be 5. I made a mistake somewhere, but I cannot. I think 6 is the shortest path, right? Yeah, 6 is the shortest path, so I somehow updated G of X incorrectly. So it got updated from here to here. So this 5 is incorrect. So this 5 is the problem. It is based on G of B plus the cost of the edge from B to X. Did I mistake this? Yep, I did. It's a 2. So I did make that mistake. This is supposed to be 6. So that means this is going to be 6 here. And this is going to be 6 here. There we go. Okay. So I think we have found the shortest path already. And the algorithm, if it keeps going, there's nothing wrong with it. It's not going to find, quote unquote, a shorter path. It's just going to be wasting cycles, because it's just going to pick E out of the set O, not find the shorter path, and it's going to pick O, and not find. It will pick X and not find the shorter path, and we're done. So I'm going to complete the algorithm as it is stated, just to be complete here. All right. So out of E and X, we're going to pick the one that has the smallest F value. E has a F value of 6. X also has a F value of 6. So they're equivalent. You can pick one or the other. So we pick, which one do you guys want to pick? X. Okay, let's pick X. Okay, so once you pick X, then you have to remove it from the set O. So the set O only has E left. And if I look at this graph here, X has no outgoing edges. So that means there's really nothing to do for each loop. So now we go back to the outer loop. And according to that condition, it is still true that some F value is less than the G of X. So that means we cannot conclude yet. So we have to pick the last element E from this set, so that now it becomes an empty set. But then we have to evaluate all the outgoing edges of E. the only outgoing edge of E is this edge EX. So now we have to evaluate X as a neighbor. So X is my neighbor. And then we have to compute the value of T, which is G of E plus the distance of the edge EX. G of E is 5. And then the cost of that, the distance of that edge is 1. So it becomes 6. So I'm going to compare 6 with the current G value of X, which is also 6. 6 is not less than 6, so that means we do not go into the conditional statement. There are no other outgoing edges from vertex E anymore, so that concludes the for each loop. And then we go back to the while loop, and at the while loop, O is now empty, and we can now stop. In other words, the algorithm is not as optimal as it can be, but it is not wrong either. It just explores vertices that are definitely not going to give us a shorter path. Yep.
So this algorithm here, it gave us two shortest paths, right?
Nope, there's only one shortest path. So what we do now is we look at previous in order to give us our quote-unquote E prime, okay? But it's not called E prime, it is called E and then suffix, or subscript, SX, because it only consists of the edges that will kind of show us how to go from the start vertex to the destination vertex. So according to this, okay, so I'm just gonna write it here. So ESX is going to be, basically what you do is you reverse all the tuples, okay? So we have A, start vertex to A, because the previous of A is the start vertex. And then the next one is AB, because the previous of B is A. And then the next one is, oh, okay, I guess this one needs to be there too, even though it doesn't lead to the destination, but it is still in the graph. And then we have BX here. So the BX is also in the solution graph. So this is ESX. So when you make a graph out of V and ESX, that becomes your solution graph. So it does contain edges other than the shortest path from the start vertex to the destination vertex, but you can guarantee to get back to the shortest path if you start from the destination. There's only one edge going into the destination vertex in ESX. So if you go from X back to B, go from B back to A, go from A back to S, that is your shortest path. So do we have any questions about the A-star algorithm? The solution of the A-star algorithm, even though it can contain edges that are not related to the shortest path, it is still guaranteed to give you a forest. In other words, there should not be two paths going from vertex to another vertex. There should be no loops of any kind. It's just that other than the shortest path, it might still contain some edges that are not relevant. So, any questions about the A-star algorithm? No questions? Yep, go ahead.
Is there any big advantage to A-stars
Over the Dijkstra's?
Yeah.
Yes. So A-star is preferred if you have a informative heuristic function. So if the function h is giving you a relatively accurate underestimate of the remaining distance from a vertex to the destination, then A-star potentially will give you a more optimized execution time, because it's not going to go back and look at vertices that are definitely not going to work out. On the other hand, if your heuristic is not informed, or it is just not really useful, it's kind of random, then it can be actually worse than Dijkstra's algorithm. Think of the special case when h is 0. When the h function always maps to 0, then it boils down to basically it will explore things kind of the same way as Dijkstra's algorithm. because it is not informed at all. It becomes the same thing, which is what we call a breadth first search. But A star performs breadth first search from the start vertex. Dijkstra's algorithm, at least the way we talk about in this class, starts with the destination vertex. So that's the difference. Yep.
So the heuristic is just like some kind of, it's not arbitrary, but it's just some function. Like in this case, it wasn't like, or I guess in this case, it was just like that thing you had written
Right.
from last time. Okay.
Yeah. So in this one, it is arbitrary because the graph itself is arbitrary to begin with. If you're dealing with something that's planar, like a map or something like that, then the actual diagonal line, from one point to another point, can be your edge because that is the actual distance cannot be shorter than that. So you can use that as your underestimate. But depending on your problem, sometimes it can be very difficult to find an appropriate heuristic function, which basically makes A star no better than Dijkstra's algorithm. But in the cases where you can find a easy and quick to compute heuristic function that gives you a pretty good idea of the actual underestimate, like the map problem, then A star algorithm is going to outperform Dijkstra's algorithm. Save for really tricky cases like in San Francisco where you have one-way streets. So when you have one-way streets, sometimes you have to go further to find a shorter route. So save for tricky issues like that, your heuristic function typically, if it is informed, it will help you find the shortest path faster. So are we okay so far with the two algorithms, Dijkstra's versus A star? Okay, so good.
Are you gonna have like any preference on one of them that you are gonna test for, or both of them are equally?
I think they're fair game. Can you tell us that?
I can give you an exercise, on A star. Basically, you can use the same graph, okay, that you already have for the homework assignment due on Monday, and what you can do is you can make your own heuristic function, because once you have run Dijkstra's algorithm, the shortest path or the length of the shortest path from every single vertex to the destination already. So all you need to do is now to say, okay, I'm going to make up my own heuristic function because it only has to be an underestimate or the same as the actual length. So you can try out, I would suggest that you try out like at least two possible cases. One is the heuristic function is exactly the length. Okay, in other words, your so-called heuristic is not really an quote-unquote estimate. It is actually the length of the path, the shortest path from one vertex to the destination. Try that out and see what A star is going to do. The second one is to make the heuristic function 0. Okay, doesn't matter which vertex you're estimating to the destination, it is always going to be a 0. Run that one too and see how it differs, because you should see a big difference in these two cases. Is that making any sense? All right. So are there any other questions about graph theory or the two algorithms that we use for searching for solutions? Well, I got a question.
All right. What is the question?
So because this is kind of like you're in a particular state, okay, and you can look at each outgoing edge as an action they can perform, and each action has a certain cost to it, and the action causes a state change. So when you go from one state, you perform an action, you get to a different state, and then from that different state you can perform its own actions available at that state, and then you end up in another state, and so on and so forth. Is that making any sense? Another way to look at what a vertex is. A vertex is now a state. An edge is representing an action. So you can transition from one state to another state by performing quote-unquote actions. Okay, so then it becomes the shortest path is basically saying That state over there is my goal. I want to achieve that. This is where I am at this point. How do I achieve that goal as quickly as possible or as inexpensively as possible? Is that making any sense? Okay. So that's kind of cool in a way because then you can now say, okay, I want the program to do that, okay, and then each edge is an assembly instruction, okay, and so you're basically saying, okay, how do I go from here? And I need to link with all of these assembly instructions, which are very small, tiny little blocks of actions they can perform, so that eventually I end up over there. So you're looking for the most optimized way to, you know, as an algorithm to, as an assembly language program to get to the destination. So you can kind of look at it that way. It can be used to solve problems other than, maps and stuff like that. Yes.
Like maybe for like a processor, like the order of execution for like different processes. Well, actually,
That.
you wouldn't know what the state is to get.
Yeah, you would. You would know the states.
Oh.
Yeah, yeah. So that would be a applicable, applicable problem for these algorithms to solve. Okay. Yep.
So then what about IP configurations or networking? Can you use it for that as well?
What type of configuration are we talking about?
We're talking about
The routing tables?
routing tables, setting up the servers, anything.
Not so much the routing table, because if you consider the routing tables, to be static and it's already predetermined, then Astar or Dijkstra's algorithm can basically give you the best route from a start or source IP address to a destination IP address. Is that making any sense?
Somewhat.
Mm-hmm. Okay.
It's making sense, but I just have to see it too.
Yeah, so you basically, you know how much time, or the transmission time from one router to another router, right? So that becomes your distance function. And then you have a start IP address, you have a your destination IP address. If you know, all of the transmission time between the routers, that will theoretically give you the best route to go from the start IP address to the destination IP address. So yes, it can be applied in that sense in terms of routing. But when you're talking about TCP IP, which route or which way a router is going to send your packet is not up to you to decide. It is up to the router to decide, right? So because from your perspective as a transmitter, you only state where is your destination and what is the source, and each router that receives that packet will go like, I see that you want to go to New York, but I decide to route you through Austin first. Okay, so that is still up to the router to decide. But you can theoretically, say, okay, but I know the best route should only take this much time. But whether that is the route chosen by the routers in between is a whole different story. There was another hand. Yep, go ahead.
Curious about that kind of thing with infrastructures that are fairly, not to say stagnant, but concrete like that. Is it better just to run these algorithms ahead of time and then just, again, make up a lookup table or some kind of system where you're just like, okay, I'm here and I want to be over here, that would be this path, instead of calculating it on the fly?
I think the calculator on the fly, may be a better option if the distance between, or the distance function itself is dynamically updated. Traffic, for instance, is definitely dynamically updated. And I talked about this last time too. If everybody, recalculate routes, to find the shortest path at the same time, then you end up with an oscillation problem because, the GPS software on every single car is going to direct, the driver to the alternate path, which at the time was the shorter path. And then when everybody switches to the alternate path, then it becomes congested. And then when everybody updates again, it will switch everybody back to the original route. Yep.
I was going to say, could we just alter the algorithm to say to put in like an if statement, like you measured the percentage of people that wanted to do it, and so you cut it off at a certain number?
That would need an AI, basically.
Yeah.
Then you need then you're basically using a predictive, ability to say that I can project, okay, up to, if I direct up to this many cars over here, I'm projecting the future distance function is going to be this,
Right.
right?
Yeah, because I was about to say, because like that'll just be a simple fix. Like if like have another algorithm that counts so many people that tries to log in,
Mm-hmm.
and then if they do know that, so then it's like, wait a minute, just only give it priority to like the first people or the last people who logged in.
Well, but there's another way to fix that problem is, do not update everybody at the same time.
Okay.
Right? You randomize the process a little bit so that, to some people, if two routes are about the same, let's say they're off by 2 minutes out of an hour, okay? So if it is only 2 minutes out of an hour, you just randomize your recommendation. So that way, things will be less swinging, okay? Because, you're randomizing things a little bit in that case. Okay, but I still haven't asked my question. I raised my hand.
You okay?
I made a point, but I didn't ask my question.
Okay.
So my question is, can this be applied to playing chess?
Yes,
How to win a game, that sort of thing.
but it can't be applied to playing poker.
What's the goal?
I'll deal with poker and backgammon and that sort of thing later. But,
Oh, okay,
but,
sweet.
but what about deterministic things like chess? Chess is completely deterministic, right?
What about show?
The chess board at any moment is a state, right? When you make a move, you are changing the state of the board. And checkmate is basically a bunch of destination states that you want to get to. Yep.
Looking for a good chess machine or just a chess machine? 'Cause
A chess machine.
then yeah, totally. I mean, you could just
National or
go
No.
from the king to any one of your pieces and decide which one of your pieces is closest.
Right,
no,
but that
they,
graph. So yeah, go ahead.
I was gonna say, but if you do that, then if it's a smarter AI, then because it has layers. Because, like for example, if that piece is available and it is a blunder or a miscalculation, the better machine would just take the piece and just focus on the
But
king.
again, we didn't say it had to be a good.
Oh, that okay. You got
Now, but there's one issue that makes the chess playing example different from navigation, like with a map. Go ahead.
The vertices for each piece are completely unique, at least per different type of piece,
Yes,
and
but
the distance you can travel to.
there's one bigger problem. Yep.
Don't also the pathways you can take change as pieces move. So
No, 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 no. That doesn't change.
pieces move.
Nope, no. That it's not that problem. Yep.
In this, are you defining each vertex
Vertex. Uh huh.
as the state of the entire board?
Yep. So you basically look at the entire board, and you can even add whose turn it is as a part of the state. So this way, every single possible state can now be represented as a distinct vertex in the entire graph, right? Because you got to know whose turn it is, because that changes a lot of things. So you basically have the position of each piece, okay, the presence or absence of each piece, the position of each piece, and whose turn it is to play. That captures every single bit of information that you need to capture for the entire state. But that graph, it is a graph, okay? It is still a graph, but there's one big difference between that graph and the graph that we have been talking about, because every other move is not yours. Okay? Your adversary is not going to help you optimize his or her defeat. Okay? It's not like you play your move and go like, you tell your opponent, go like, I think you should make that move.
oh, then you do space opposite.
So, yep,
So in a sense, like the paths would change depending on what your adversary did. Like
correct.
the cost.
Yeah, but that changes the whole thing, of the shortest path, because the assumption that you are controlling every single edge is no longer true. You're controlling alternating edges, but there are edges in between that the other side is trying to oppose or trying to counter. Yep.
Would it work just as well or worse if instead of having it to where the entire graph has both my moves and my opponent's moves, but instead only my possible moves, like everything is treated as mine, and every single time it's my turn again, I have a new starting vertex that is the current board. So the graph only considers moves that I can make,
But how do you take into consideration what your opponent is going to do?
Like the graph updates, like
Hmm?
with every step, like the graph would update.
But then
It's like this algorithm wouldn't really.
that would
Wait,
not.
wait, hold on for a second. So every time you make a move, it will make like you probably have to put in a binary tree, man, to see what all the
Well, okay. So as it turns out, there's a name for this entire class of problems.
wow.
It's called. Okay.
Game. Don't tell me game. Come on, man. Come on.
No, this is actually called game theory. Okay, so game theory is the underlying study of playing of this type of problem where you have an adversary. Okay,
Right.
okay, and the representation is what we call a game playing tree. Okay, it's kind of like a tree because everything is just branching out, and occasionally they do merge too, but we usually just look at it as a tree. And there are special techniques in game theory to deal with those type of trees. There are trimming techniques, like you can trim off an entire tree or an entire scrub if you want, by looking at certain values. So it's also called alpha beta trimming. That's a very well-known technique for looking for the shortest route to victory in a game tree. So if you conceptually, if you can have a program that can work out all your possible moves, what your opponent can possibly do, to each move that you make, and then how you can counter each one of those, possible paths, and you say, okay, you've performed that deep search, and then you get to an end state that is your victory, okay? And you can find the path where no matter what the opponent is going to do, it will still be your victory. That means whatever action that leads to that particular bunch of branches is the proper move, is your best move. Is that okay? So in theory, it is possible to basically say before the chess game starts, the outcome is already predetermined, because if you can look ahead that far, okay, to finish the entire game on all possible ways to end the game, then it can boil down to just the first move. The first move, or who gets to move first, can already predetermine the entire game. Now, that game is fun for people because we do not have the computation ability to figure out all the possible, states and how, each branch can potentially end. So that's why, for humans, it is a fun thing to do. But to computers, it is completely deterministic, with any type of processor that has enough processing resources to finish the entire path all the way to every single way to win the game. Yep.
Isn't that when a game is defined as being solved? Like Connect 4, for example, is solved because the game is decided solely, like if two perfect people were playing,
Yep.
the game is solved because the first move is the only one.
I believe that is the terminology. Tic-tac-toe is solved. Okay, tic-tac-toe with
I don't think it is.
Isn't it proven that like if you go first, like if both people are perfect, like whoever goes first wins?
in a chess game.
Yeah. No, Connect 4 and Yu-Gi-Oh.
No, not you.
Okay.
Yu-Gi-Oh.
So I do not know I don't know the current state of the art for a chess game. I don't think can actually completely determine the entire path yet.
I mean, can it like be theoretically like?
Theoretically, yes, but we may not yet have the processing power to do it yet. But every year, we get closer to that, to that end goal. And that's why, 10 years ago, computers can play chess, and they can only match up to a certain level of human players. But every 18 months, the computation power doubles for the same amount of money, right? So that tree gets explored deeper and deeper and deeper, and that's why at this point, computers can beat master level chess players. Not all the time, but but
I was about to say, but chess is finite. There's only like 2,770 effective moves that you can do in chess.
yeah, but the branching is the killer, because the branching means from each position there are so many possible moves. Yep.
Yeah, because there's some weak and strong squares. Like if you Yeah, well, because it can't.
Yeah, but I don't think it's a solved game yet. Yep.
With a theoretical, like, God level processor,
Mm-hmm.
What the heck?
isn't all or aren't all games without any random elements technically, like,
No,
theoretically?
no, no. You have poker, right? You got poker and other games that have deterministic, that have non-deterministic characteristics to it. Now, okay, so since we're talking about chess, there's another game that is, the game itself is deterministic. There's no dice throwing. There are no cards. No go. Exactly.
Yeah,
So that is an interesting one because that game is far from being solved.
yeah, it is.
You know,
Just go find that move. They count 200 and something thousand effective moves,
exactly.
and it's still going.
So you can basically look into articles that talk about the Go game versus chess.
Yeah,
Now Go is a killer because of the lack of a lot of rigid rules. This piece can only go diagonal. This piece can only go straight. This piece can only go da da da. Go goes like you can place your peg anywhere you want. So that increases the branching factor to no end. And then the board is also a lot bigger too in terms of number of positions. So Go is not even close to solved, even though it is completely deterministic. But computation-wise, it is almost impossible using current hardware to really get that game to be computerized. I mean, it's not even. Yeah, go ahead.
Could we just create some machine learning setup that defines the edges as it goes and plays itself forever until the game is solved? Or will we move?
It is possible, just like an AI can teach itself how to play Dota. Okay. Now, so how do you compare Go, chess, and Dota? I mean, Dota is deterministic. It really is deterministic.
yeah, but Dota's a little bit harder than chess, though.
Hmm?
And go, probably.
Dota is a little bit harder than chess, but not. But Go is harder. Dota is easier than Go, though.
Probably not.
Go is harder.
Yeah, Go is harder. Yeah.
Go is harder than Dota. Because if you look at the branching factor, Go actually has a larger branching factor compared to Dota.
Dota is finite, bro.
Yeah, because if you look at Dota, at any moment, what moves can you make as a next move is actually somewhat limited compared to Go. Yep. The more rules there are in a game, the more restrictive it is, and the better the computer can play it. The fewer the rules, the harder it is because computers go like, the branching factor just goes to like that. Okay, so what about the other games? Okay, let's backtrack a little bit here. Let's look at backgammon. Okay, backgammon. Now backgammon, I don't even play that game. I just.
don't even know how to play myself, so I don't have.
But backgammon is not a adversary game. There's no second player. You are doing it yourself. It's a single player game, but the problem is it is deterministic. It's non-deterministic. You have to throw a dice. So there's a chance thing now, right? So you can make a move, but the possible states that can come out of quote unquote one single action is many, and then there are no probabilities associated to each branch. But as it turns out, the moment you throw in what we call stochastic or undeterministic factor into the graph thing, A star doesn't work anymore. Dijkstra doesn't work anymore because it is undeterministic. Okay, and that was kind of the focus of my dissertation, like 20 something years ago. Yep.
I would imagine checkers
Mm-hmm.
already been,
Solved.
yeah, right.
Mm-hmm.
And it is deterministic on the first move, is it?
Yep. Yep. Checker is deterministic. Othello is actually easier compared to Go also, even though those games are kind of related in some ways, but they are not the same. Yep.
Because I was about to say, with checkers, if the AI is programmed by a good checkers player, because I think it was the one in theory, the one who goes first usually wins. But if the adversary, the AI or whoever's playing knows that, can they just set it up to have a tie each time and just because
Like tic-tac-toe.
yeah,
Yeah.
that's what I was asking.
Yeah, tic-tac-toe is solved because in order not to lose a game, you can always make a game tie basically. with tic-tac-toe. And in many other games, it's the same way. You can always get a stalemate or basically a tie, so you don't lose the game. Even if you don't get to move first, you just tie the game.
Right.
Yep.
Oh yeah, so I was sort of wondering what that comparison would go in like Dota, or I guess like any video game for that matter. Does the fact that like Go Go is like turn based, right? I know nothing about like the actual.
Go is turn based.
But it's
Yeah,
turn based.
it's turn based.
Whereas like most competitive video games are like real time. Like does that like matter at all for like how hard it would be to I guess win?
You have to look into the game engine itself and see how it takes the input in order to determine the next state. Um, but most of the video games are not undeterministic. Some are. Some will throw into like a undeterministic probability into it. So that makes it a little bit harder to deal with. Like even backgammon, which is not, it's a single player game, but A-star and Dijkstra's algorithm cannot be applied to backgammon because of the undeterministic factor of it. Yep.
What about like shipping and stuff like that when you order something online and like
Mm-hmm.
if you track the package, sometimes you could see like it, even though you might be like one state away, it could like take like an entire loop before the package like actually gets to you. Does it use any of those? Does it use either A-star or Dijkstra's algorithm, or does it have a completely different thing?
I do not know because the it depends on whether the distance function is actually kind of deterministic. Can you estimate, how much time it will take for something to go from the, let's say, San Francisco distribution center to the Sacramento distribution center. So is that estimate, can it be known? Can you at least get a reasonable estimate? And if it cannot be, okay, so this is where neural nets can come in handy because you can always train a neural net based on past observations. And the best thing about the neural net is, in addition to the usual stuff that you throw in, you can throw in weather condition, you can throw in time of the year, you can throw in many other factors. So if there's any type of correlation, a neural net typically will pick it up, be able to say, oh, that is a relevant factor, these are not relevant factors, and it will give you the prediction based on past observations. The problem with a neural net is it is not going to give you a admissible heuristic. It is not always going to be an underestimate. It will give you an estimate to its best ability, but is it going to be an underestimate? No, not guaranteed to be an underestimate, which means if you use a neural net to substitute for your heuristic function, it will not necessarily give you the shortest path. But it might be very, very close, and your heuristic function can be very close to the actual length of the shortest path to begin with. So when you throw neural nets into A-star algorithm to substitute the H function, the heuristic function, then kind of funny, really interesting things can happen. Any other questions?
Rubik's cubes.
Huh? Yeah.
Rubik's cubes.
That can be solved using the A-star algorithm or Dijkstra's. Oh yeah, because you only have so many moves that you can possibly make, and then each cube configuration is a vertex. Each move that you can make, each twist that you make, is an edge, right? So you have the destination state, which is all faces are single color. Okay, that's one single destination. So yes, Rubik's cube can be solved by Dijkstra's or A-star. Now in that case, you can probably even come up with a reasonable heuristic function by counting the number of tiles on each side that are the same color or something along that line. So you might be able to generate a heuristic function that is easy to compute, guaranteed to be an underestimate, and utilize it to help you find the solution quickly. Yep.
Is there like a limit to the number of vertices to which it's no longer worth trying the algorithm because it'll take too long? Where is that wall?
Okay, so what you're looking at is, so what you're looking at, or what you're looking for, is the time complexity of the A-star algorithm and also the Dijkstra's algorithm. And I believe both algorithms, the big O, okay, right there, worst case scenario is big O of V, the cardinality of V for worst case space, which means how much space it's going to consume, because that is just determined by the O set. But in terms of time, it is proportional to the number of edges. And I believe Dijkstra's is the same way too. Dijkstra's is also bound by the number of edges. So now it depends on how many edges are we talking about. Because you can degenerate a graph to a single line, right? So the number of edges is kind of the same as the number of vertices. So it becomes a very short algorithm to solve.
So same like how you mentioned with chess, how it's the branching that really.
Right. In the worst case, the cardinality of E is proportional to the square of V, the cardinality of V. So that means in the worst case, the worst case performance is, you can kind of say it is bound by the cardinality of V squared, because that's the number of edges you can possibly make. Everything is interconnected by edges, and that's basically the worst you can get. Is that okay? So the branching factor is the killer, because if you are dealing with something that has let's say even a billion vertices, if the branching factor is just 1, every vertex can only connect to another vertex by one single edge, it's not that big of a deal. Easy problem to solve. On the other hand, if you have an almost completely connected graph where every vertex is connected to every single other vertex, then you have a pretty big problem to solve, because now you have 1 billion squared as the amount of time to solve it. So that becomes much more difficult to deal with. But these are not called intractable problems, because it doesn't involve factorial or anything like that, so they're not called intractable. When you have the salesman traveling problem, then it is intractable. Do you guys know which word I'm talking about? Intractable? Okay. Intractable. Okay, so Wikipedia says, hard to control or deal with. Basically, they are problems that we do not have known efficient algorithms to solve. Yes, we have algorithms to solve those problems, but they cannot be done in a reasonable amount of time. And optimizing the traveling salesman route to go through a fixed number of cities is one of those problems. Well, that's on a bicycle. So, any other questions, related questions to state space search? It's kind of only the beginning, of this kind of problem solving, because we have game theory to deal with a related but different problem, where you have an adversary who's trying to counter your moves, all the time. And question? Oh, okay, just stretching. Okay. So in game theory, okay, I'm not going to get too much into game theory, but in game theory, there's a technique called alpha beta pruning. So basically, there are ways to make it faster to compute. Instead of searching exhaustively, you can basically say, oh, there's no need to explore that branch, because what I already know is already better than everything that can possibly on that side of the branch. So you can basically prune that branch entirely. We got 2 minutes left, 3 minutes left, so I can talk about this. What if you have a problem that can be solved by A star, okay? But you have a limited amount of time before you have to make a decision. So let's say you have a problem which is a robotic problem, okay? So you have to activate some kind of thing to make a decision and go like, okay, I'm either going this route or going this route, okay? But you have to make the decision within, I'm just going to give you a number here, 5 milliseconds. But the problem involved, if you run the entire Dijkstra's algorithm or A star, is guaranteed to take 10 milliseconds, which is the time that you don't have. So what are you going to do? It takes at least 10 milliseconds to run Astar or Dijkstra's algorithm to give you the best optimal path. But in real time, you have to make a decision within 5 milliseconds. So you don't have enough time to find the shortest path. Yep.
Can you interrupt it when it just finds a path?
But even that amount of time is not guaranteed. So there's no guarantee of when Astar can give you a path. So, yep.
Do you know the number of edges that we have?
Nope, you cannot do that either. So for that, we have a different algorithm. It's called C-star. Okay, me.
B-star, Professor.
Hmm?
Up in the B-star.
There's a D-star.
Wait, what happened to B?
Okay, so these algorithms are called, they're basically iterative. They resemble depth first search, but with a limited depth. In other words, it's iterative. In the first iteration, it's just going like, let's just explore one edge away from the start state, okay, and see which edge looks the most promising to us. Okay, that was done in half a millisecond because it's really easy to do. Okay, now that I got enough time and I have one decision already kind of in the pipe, now let me explore 2 levels deep, 3 levels deep, 4 levels deep, and so on. So by the time you have done like 4 level deep your search, come up with an answer, we ran out of time. So you just make your decision based on the best estimate at that time. And these algorithms are basically guaranteeing that each iteration doesn't take too long. It doesn't give you the best solution possible, but it will give you a solution. It will give you a suggestion. But the more time you have, the deeper you can go, and as a result, the more accurate or the closer the choice is going to get you to the actual optimal solution. So it's interesting because these are used in real-time problems like robotic stuff, because you have to make a decision one way or another. Are you going to kick that prune out of the air path or not? We're talking about prune sorting, which is automated. That's really kind of interesting because they use a pneumatic mechanism. So they throw these fruits, nuts, and whatnot into midair, and then they have several cameras to look at that thing in multiple angles, and then they will analyze whether that prune is good enough to be sold, or does it have to go to the other bin to become prune juice. Okay, and if you just kind of imagine this, you have a basically pneumatic machine gun, okay, shooting these prunes, go like that, okay, and then when they're in midair, these cameras will take the pictures all in real time, okay, and somewhere along the quote-unquote trajectory, there are actuable jets of air, and that's how they can direct the prune to go into one bin or another bin. So you're basically thinking boom, 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 like that, and then you have these actuated pressurized air to go like poof, 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 to sort prunes and other fruits into different baskets, and it's fully automated. And this technology was actually available in the 90s.
Oh my goodness.
Yeah, even in the 90s, they were using technologies like this. So I'm just putting that out because I was just kind of talking about the real-time decision thing, because whether you actuate the puff or not is a decision, and you have to make that decision. Now, occasionally you might throw a perfectly okay prune into the prune juice basket. Okay, you wasted one prune, but it needs to be done, right? I mean, you can make some mistakes and make it non-optimal, but you have to get the job done. Yep.
I was wondering if these kind of algorithms are used in augmented reality, because they would do scanning and they would find the distance between the objects to actually generate an image on the screen. Would that be a place for it to be used something like that?
It might be, but augmented reality is more of a user interface issue compared to the actual nature of a problem. But I think in self-driving cars, they have a lot of AI stuff that needs to go on. In other words, if an automated car knows that it cannot avoid an accident, okay, what is it going to do? How is it going to make a decision? Well, according to Mercedes, it will protect whoever paid for the car first. You can look it up. It's actually on the internet because somebody interviewed an executive from Mercedes-Benz and asked that sensitive question. It's like, okay, in a case where an accident cannot be avoided, what is the algorithm that your car is going to use to make that decision? And Mercedes-Benz, or at least the executive said, we are going to protect the occupant of the vehicle, which may not be the best possible answer. Because they're basically saying, if you pay for the car, we're going to protect you.
Damn, man, that's like the mafia, man.
That's how we drive anyway. So
Mercedes,
Look it up.
self-driving crash.
you gotta add a morality core to the.
Wait, you can't put a sen- you can't make it a sentient individual intelligence.
There we have it.
Over by standards.
Wait, what? Okay, like when Mercedes no more, there's someone just cruising one day, right? And a hater just come out of nowhere.
Well, I think these days, driving can become. I think these days, driving is no longer a A-star or Dijkstra's problem. It's now becoming a game theory problem. And then we'll have AIs battling it out on the road. It's like, who can get to the destination first? I'm gonna cut you off.